The Department of Conservation has estimated there's about 35,000 tahr on public conservation land. I've heard quite a few questions about whether that estimate is correct or not, and some concerns about how the number might have been derived. Some people have even expressed the opinion that the numbers are made up. In fact, they are derived by a scientific process, and this video outlines what that process is. The Department of Conservation's got a tiered monitoring system, and the highest tier in that system is what's known as Tier 1. Tier 1 consists of a series of sites across all public conservation land, and it's essentially an 8 kilometre by 8 kilometre grid. So each site is 8 kilometres away from the next site, and there's about 1,400 sites located across public conservation land. Those sites are not all surveyed every year. In fact, they're done on a 5-year rotational basis. In sites that are in tahr management units, there's some additional work done to count the number of tahr in a 2 kilometre by 2 kilometre area adjacent to each plot. Those counts were undertaken on 16 plots in 2016 and on 22 plots in 2017. And it's those 38 plots that provide the data that yield the 35,000 tahr estimate. The statistical analysis was undertaken by David Ramsey at the Arthur Rylah Institute in Australia. You can download his report off the DOC website. Also available on the DOC website is the raw data that underpins David Ramsey's analysis. It's downloadable as 2 Excel spreadsheets, one for each year, and so that covers the surveying in 2016 and 2017. Each of those sheets specifies a Tier 1 plot that indicates where the survey was undertaken, and you can go to this URL here and discover a bit of information about each of those Tier 1 plots. In this case, I've selected AR136. You can do that in 2 ways, either through the drop-down menu or by clicking on the dot on the map. AR136 is one of the plots that David Ramsey analysed for tahr abundance. When you go to that site, you get a bit of information on the physical aspects of the site, and there's a wealth of other information there. Included amongst that is the presence of faecal pellets from ungulates, and in this case we can see that there were faecal pellets present. What we don't know from this is whether those faecal pellets were from tahr, chamois, deer or sheep. The data provided by DOC are quite rich. Here's an example of some of the information that's available on those spreadsheets. Again, looking at AR136, there were 3 counts done. The first count was undertaken on the 2nd of March 2016. That was an evening flight. There wasn't much wind. It was 9 degrees. Visibility was unlimited. There was no rain. And on that flight, they spotted 21 tahr, one of which was an adult male. And here's where they saw them. AR136 is in the very head of the Dobson River, due south of Mount Sealy. Each of the red dots on this diagram illustrates where tahr was sighted, and in most cases multiple tahr were sighted at each of those red dots. Here's a complete list of the sites that were sampled by year, and they are divvied up by tahr management units. In some cases, only 2 sites were surveyed within a management unit. So for example, MU1, AR130 and AV131 were the 2 sites that were sampled. In other cases, up to 6 sites have been sampled. So that's the case for MU2, MU3 and the Southern Exclusion Zone. So how did Doc take that observation data about the number of tahr that were at those sites and turned it into a prediction about the total number of tahr? Well, we're going to look at a hypothetical site to understand that. The study site's overflown once and the number of tahr sighted is recorded. And we're going to keep it really simple. So we're going to assume that tahr don't move in or out of that particular plot, and there are no births or deaths. And given the time of year that these observations were undertaken, births is certainly not an issue. As far as the other aspects go, Doc's process does deal with those things. It's got some mathematical approaches for dealing with movement in and out of the area and deaths. We won't go into the details. What we want to do here is actually get the concept of how Doc were able to estimate the number of tahr. Core to understanding how they did it is the idea that not every tahr is seen on every flight. So P is the probability of detection. Let's assume that P is 0.5. In other words, we're going to see about 50% of the chance, 50% of the tahr on any site on any flight. You can look at that another way and say we've got a 50% chance of seeing any particular tahr. What that doesn't mean is that on each flight we'll see 50% of the tahr. On some flights we might see none. On some flights we might see 100% or 20 or 70 or whatever. So this is just like going hunting. Some days you're on, some days you're not. We don't know what's going to happen until we're out there. Now suppose that we saw 10 tahr in our overflight of this particular site. We know immediately that there are at least 10 tahr on the site, but we don't know how many we missed. And that's where we have to get into the statistical analysis. Here's what we know. There's some number of tahr on the site, and the minimum is 10, but it could be more. The probability of sighting tahr is 0.5. Now I want you to assume for the moment that the actual number of tahr that are on the site is 10. Well, the chance of seeing 10 tahr when 10 tahr are present and P is 0.5 is 0.001. That's one chance in 1,000. In other words, it's extremely unlikely there are only 10 tahr. Another way to put that is to say it's the same odds as flipping a coin 10 times and getting 10 heads in a row. That just doesn't really happen. Let's change the assumption. Suppose there are actually 11 tahr on the site. We saw 10. Well, if there are 11 present and we saw 10, then the chance of doing that when P is 0.5 is 0.0054. Hey, that's 5 times more likely than if there were 10 tahr on the site. So what we know immediately is that it's more probable that there are 11 tahr than there are 10 tahr. But that probability that there are only 11 tahr on the site is extremely small. We'll carry on that experiment. Along the horizontal axis of this particular diagram is the number of tahr that are on the site. And on the vertical axis is the probability of seeing 10 tahr if that number of tahr are on the site. And the number of tahr on the site that's most likely to yield 10 observations of tahr is 19 or 20. But that's not a whole lot different in likelihood than if there were 18 or 21 or even 17 and 23. It's the most likely given what we've got. If you had to make a guess about how many tahr were actually there, you would say most likely number is 19 or 20. What we do know is it's extremely unlikely that there are fewer than 13 tahr on the site, and it's extremely unlikely that there are more than 31 tahr on the site. The probabilities are tiny of observing 10 tahr if those are the actual number of tahr on the site. Well, it would be pretty good if we could narrow down the numbers that we think might be on the site. The way we do that is by undertaking more observations. We're going to assume that there are 2 other flights. On the second flight, we see 8 tahr, and on the third flight, we see 15 tahr. Well, that's pretty helpful because now we know there are at least 15 tahr on the site, whereas before we thought there were at least 10. So we've got some more information there. This maximum observed number method is quite common as a wildlife census method. It's been used widely in New Zealand where observations have been made by 2 or more observers, either from the same site or from the same observer multiple times from the same site, to estimate the number of tahr in a particular location. The highest number that's seen by any observer or by on any time by the same observer is assumed to be the number of tahr that are on the site. So we know there's at least 15, but just as before, there could be more than 15. So let's see how we deal with that. We go through a very similar statistical process and we work out the joint probability of seeing 10 tahr, 8 tahr and 15 tahr with p equal to 0.5. And we end up with this particular picture here. Now this picture's changed a little bit from the one that we saw before in that the peak has shifted to the right. The most likely numbers now are about 22 or 23. So that's gone up. That's because of the 15 that we observed has shifted the expectation to the right. But the tails have come in a bit. Whereas we had tails out to the right, 31, 32, 33 before, they've just about disappeared. And the tail at the left, 15, has become negligible, and numbers smaller than that have disappeared. So it's worth comparing these 2 distributions. The brown distribution is from the single flight in which 10 tahr was seen. The blue distributions from the 3 flights in which 10, 8 and 15 tahr were seen. This picture clearly shows how the peak has moved to the right, but also how the tails have come in. So now we have a narrower confidence interval for the number of tahr that are likely to be on this particular site. Of course, those predictions were highly dependent on P, and it turns out that P is very critical. We'll illustrate this by going back to our first flight where we saw 10 tahr. Now if P is 0.4, that's the blue curve. That's the one out to the right. It's pretty flat and it's fat. So the most likely number when P is 0.4 and we saw 10 tahr is that there are 24 tahr on site. And the confidence interval is pretty broad. However, if P is 0.6, that's the red curve. The most likely number now has decreased to 16 and the confidence interval has come in. It's a narrower, peakier curve. The same thing happens when P becomes 0.8. The most likely number, smaller again at 12, and the confidence interval is quite narrow. Of course, when P equals 1 and we saw 10 tahr, then we know that there's 10 tahr on site. There is no curve, there's just a single vertical bar at 10 tahr. So it turns out that knowing P is critical, and the higher P is, the more information we get about the likely number of tahr, or the more precise our estimates are for the likely number of tahr based on the number of observations that we have. So the big question is, how on earth do we find out P if we don't know how many tahr there are to begin with? Well, it turns out that it's not too different to what we did before. We survey each site multiple times, just like before, but we survey many sites. And what that allows us to do is to calculate the joint probability of observing the numbers of tahr we saw on each flight at each site for any given P. And we undertake the analysis by changing P, and we find the P that's most likely to generate the observed pattern of responses. I'm sure you'll understand that the maths is reasonably complicated. David Ramsey provides quite a bit of information as to how he went about doing that. I won't go into the maths. What's important here is that we've got the concept under our belts. So what do the data look like? Well, over 3 flights, there were 26 plots where tahr was seen out of the 38 plots that were surveyed. So, not all plots had tahr on them. And over those 3 flights, a total of 1,960 animals were seen. The vast bulk of those were tahr, 1,287 tahr, and about 10% of those were adult males. What's interesting, given that this was all on public conservation land, is that the second most common animal seen was sheep, with 340 sheep. So sheep outnumbered chamois and deer combined. And there were also some cattle seen. David Ramsey was able to take all those observations, go through the sort of analysis that we've just outlined, and come up with his best estimate of the number of tahr on public conservation land. And we need to be very careful here to reiterate that this is tahr on public conservation land. None of this work was undertaken on pastoral lease or private land outside the conservation estate, and so the 35,000 tahr is not the total number of tahr that exist in New Zealand. They're simply the number of tahr on public conservation land. However, it's important to note there's quite a bit of uncertainty around that estimate. David Ramsey was able to use some complex statistical analyses to derive a 95% credible limit for the number of tahr. So this is essentially says that we can be 95% certain, or in other words, there's 1 chance in 20 that the number of tahr is outside this range. And so 95% is from 17,000 to 54,000. David Ramsey was also able to estimate the P, the mean detection probability, across all the management units, and that was 0.43. As with the total abundance of tahr, there's a 95% credible limit to that. We can't say it's exactly 0.43. What David Ramsey estimates is that the mean for P is somewhere between 0.31 and 0.55. However, that varies by site. Some sites are vegetated more than others. Some sites have a lot of gullies and caves and rock crevices, and others are wide open and easily viewed. So P varies a lot more on a site-by-site basis than on the than across all sites, and his estimate there is from 0.16 to 0.74. One of the opportunities to come from this research is to compare the estimated mean densities of tahr within each of the management units, shown in the second column here in black, with the target density specified in the Himalayan tahr control plan shown in blue. As Dave Ramsey points out, for each of those except management unit 7, the mean estimated density exceeds the target density. What we've been able to do so far is show that statistical analysis can make inferences about what's most likely and the confidence of predictions. That does require a lot of data, and there's only been 2 years of analysis undertaken. It takes 5 years to get around all of those tier 1 plots. There's been more analysis undertaken in 2018, but those data haven't been released yet, and we don't have the revised estimates on those yet. What we would expect is that the credible limit will narrow down as we add more sites to the analysis. But we're still left with a question. How good are these estimates? 35,000 tahr, somewhere the 95% credible limit, 17,000 to 54,000. Is that a good number or not? Well, that's too much for us to answer today, so I'm going to leave that for another video that we'll come back to soon.